Now let's go to this one. To get from this one to that one, I can just see that I've replaced that chlorine with a hydroxyl group. In this case, if I just use sodium hydroxide, my hydroxyl group is also a strong nucleophile. What do we typically call sodium hydroxide? A base, right? It's a caustic or basic solution. It's also a nucleophilic. So strong bases are also typically strong nucleophiles. Vice versa isn't quite true. But if you have a strong base, it can be a nucleophile also. How about this one here? 1-iodobutane. Oh, we just did that problem, right? I'm going to use sodium iodide, right? Okay. How about if I replace that iodine with a cyanide? Again, I just use sodium cyanide. Okay. You need to be able to identify the nucleophiles depending on what your product is. You can imagine if you were a synthetic chemist and I needed to put a cyanide molecule, C triple bond N, I could do that if I just found some way to put a halogen on there first. And then I know that's where it's going to react, okay? Because it's going to do an SN2 reaction. Having said that, it typically, again, has to be a primary halogen for the SN2 mechanism to form that product, okay? And this one, sodium acetylide, I actually added a carbon, triple bond carbon there. And finally, I have an oxygen plus 2 methyl groups. That looks like sodium ethoxide. Okay, sodium ethoxide. Notice that I just put ET there. That implies ethoxide. If I put HOET, that implies ethanol. Okay, ET is very common. If I put OME, that implies sodium methoxide. It's very common to see that also. Different terms used for the same compound. And finally, I just use excess ammonia to put my amino group out here and do an SN2 reaction on my chlorine. Okay. Yes, Gina?
So when we did the sodium ethoxide one, we ended up adding carbons to our long parent
We
chain?
added 2 carbons. 1, 2, ethyl group here.
Okay.
That is, yeah. Yep.
Okay.
That makes sense? Ethyl ethoxide. Let's go on. Let's just take one quick look at SN2, what makes a good SN2 reaction. Strength of the nucleophile means strong, right? Typically, if it's a strong nucleophile, it's also a strong base. Okay? If I look at polarizability, that's where that iodide comes in. It's actually very polarizable, so it makes a good nucleophile. Steric effect. If I have a bunch of big bulky groups onto it, it typically is not a very good nucleophile because it just can't get in there. And also solvent effects. If I were looking at solvent effects, if you look through the chapter, it says for an SN2 reaction, I want to have aprotic polar solvents, okay? Because it will actually stabilize the nucleophile, but it won't, because if I had polar solvents, I tend to stabilize the carbocations, and then you usually go by an SN1 or an E1 reaction. Yes?
Sorry, this is probably a stupid question, but what does aprotic mean?
Aprotic means no proton in it. Like methanol
Okay.
has a proton on it. Acrylonitrile does not. It's different solvents depending on where they have protons.
Okay.
Typically when we talk about protic solvents, we talk about water or we talk about alcohols.
Okay.
Those are the big ones. Because they can hydrogen bond, right?
Okay.
Okay. And finally, we need to also look at the substrate itself, the carbon compound, the alkyl halide. I need to have a good leaving group, which are typically chlorine and bromine. I also have to have it on the primary carbon, typically for SN2, because I need to get in there. And also, what happens when I do an SN2 reaction? I have, what's the name of that guy that has the inversion again? Walden. Walden inversion. Okay. So let's just take a look at sort of the common strong nucleophiles. Iodine, we talked about that one. We talked about cyanide, we talked about hydroxide, and we talked about methoxide here. There's also a counter ion to all of those, right? The book lists a few others, but we don't do many examples of those. Yes?
Okay, sorry, one last one.
So
in the
there's always one last.
I know. Okay, in the SN2 reaction, the first one, we used alcohol. And like the first
That's
example.
not an alcohol, that's hydroxide.
Oh.
There's no carbons attached to that.
So for carbons to be, oh, perfect, that makes so much
Okay,
more sense.
does that make
Okay.
sense?
Yes.
If I have just OH, that's hydroxide. If I have HO and some alkyl group, that's an alcohol.
Okay,
If I rip off that hydrogen off the alcohol, that is alkoxide, a methoxide or ethoxide or something
Okay.
like that.
thank you.
Okay. If I look at weak nucleophiles, I typically think of things like alcohols or water are weak nucleophiles, okay? There are a bunch of other ones here too, but these are sort of the big ones. It's a lot easier if you're talking about the strong ones. If you know the strong ones and the weak ones, and then in between, it's hard to tell because you don't know what's going to happen, right? Okay? So let's actually look at the mechanism one more time. Again, if I take an alkyl halide that has stereochemistry, I have 4 different groups attached to that carbon, that is actually a chiral carbon. When I go through the transition state, I actually invert the stereochemistry. Does that mean I always go from an R to an S? No, because R and S is just nomenclature again. If I have a higher priority coming in, I might actually have the same nomenclature depending on what's coming in, right? It really depends, okay? So I still have, from an actual geometry standpoint, I invert the stereochemistry, but you still got to go back and make sure that here is S and this is not S or R. It depends on what that group is because the nomenclature system is just based on priorities, right? Okay. So let's look at the SN1 reaction, okay? If I look at the SN1 reaction, my rate limiting step in this case is the fact that I'm just going to lose that halogen, and I'm going to lose it because typically that carbocation is somehow stabilized. If I have a protic polar solvent, I tend to go by SN1 reactions rather than S1, SN2, or if I have a tertiary alkyl halide, I know that my tertiary carbocations are more stable than primary, I tend to go by SN1 reactions. If I were to give you a starting material and a product and you saw some sort of rearrangement, you know it had to go by an SN1 reaction, right? Because only carbocations can undergo rearrangement. SN2, they just go inversion. You don't have any carbons or hydride shifts, right? Okay? So if I look at this one, it is actually unimolecular. That just means that its rate only depends on how fast that halogen can leave to form the carbocation. That's my rate limiting step. And I can actually show that. Here's my starting reactants. If I go up here, I have a fairly large activation energy. Once I activate it, I form a fairly stable carbocation. Okay? That's a very slow step. Once I get here, I can either go back, or I could go forward and actually react with my nucleophile to actually form a stable product. So my rate limiting step is just getting to here, and then I can either go forward or I can go back. In this case, we call that an intermediate product because it is actually isolatable sometimes, and it's actually a stable compound. In that case, it's my carbocation, okay? So this is my reaction intermediate. Once I form that, I then have to very quickly, any nucleophiles that are around in solution will tend to react with that carbocation. Okay? So I first have to form the carbocation and then I react. Okay? So first order, only because it only depends on my starting materials. It doesn't depend at all. The rate doesn't depend at all on what my nucleophile is. But typically that means I have to have a poor nucleophile. Otherwise I'll go by SN2, right? But I have to have a poor nucleophile. Otherwise it will react and kick off the bromine and SN2 reaction. Okay? If performed on an asymmetric carbon, meaning if that's a chiral carbon here, if I form a reaction intermediate that is a carbocation, I can react from either side of it. We'll show an example of that. So I form a racemic mixture. What does that mean, racemic? I have both enantiomers, right? I have the R and the S in equal amounts. Okay? Typically when we do substitution, SN1 reaction, there's a slight preference toward one of them, or not, only because when my leading group leaves, it's sort of in the same area, because now it's going to react quickly. That side has got to that bromine or my halogen in this case still around there, it's sort of blocking a little bit for my nucleophile to come in, so I get a little bit more of one isomer than the other, so I never usually get 100% racemic mixture, but it's close. Does that make sense? Okay. As I lose this, this is still sticking around close to this, because it reacts so fast it's still there. I would rather come from the other side a little bit. Okay? Okay. So let's look at the solvent effects for SN1. If you look at that, that is actually a protic solvent because it's got a hydrogen on it. In this case, it's just an alcohol. You can see my lone pair